2015 question number 1 starts by giving us this scenario of water going into some sort of pool or box thing, whatever. Water is flowing into the pool by R of t, a rate, keep that in mind, and water is flowing out by this function d of t. It's important to remember that as you go on with this question, that you know that R of t and d of t are rates. So the output is going to be cubic feet per hour, or getting cubic feet per hour. That being said, part A is asking how much cubic feet of rainwater is flowing into the pipe during the 8-hour interval from 0 to 8. Now this is key. First, we want to know simply the amount of water flowing into the pipe. Well, the only function that gives us a rate for into is R of t. D of t is telling us the rate at which it's going out. So if we want in, we're only going to focus on R of t. Now the question is, how much cubic feet here, but R of t is cubic feet per hour. So this is connecting two concepts together. You're going to need to integrate a rate. Because if I told you, for example, the rate, I'm going 10 miles per hour, or how much distance did I cover, I would integrate miles per hour to just get miles at the end. That's what exactly what I'm going to do here. So for part A, it's actually pretty simple and straightforward. You should remember that this is a calculator question. Questions 1 and 2 tend to be calculator-based questions. So you're going to plug this equation into your calculator, but then integrate that from 0 to 8, and you get this output here. So remember, the integral of a rate gives you the amount. So if this was cubic feet per hour, the integral would just be cubic feet. Now this question is worth 2 points, 1 point for the integral expression, and 1 point for the final answer. Part B, on the other hand, we're asked to find whether or not the amount of water is increasing or decreasing at time of 3 hours. Automatically, you know that if it's increasing or decreasing, you're going to look at its first derivative, whether it's positive or negative. Now, how can you find a function, right? They don't give you a parent function they can integrate. They don't tell you that the total amount is this much. You're only given the rate in and the rate out. So you kind of have to come up with your own equation. That's kind of what I did here, right? It seems a lot at first, but simply put, I know I'm going to need to find a derivative, and I'm going to consider R, the rate in, and D, the rate out. So to find the net change between the two, I guess you could say, I'm going to make up a function just for my use. The derivative of A of t, because remember, we're dealing with rates. These are rates, is equal to the amount in minus the amount out. So when I subtract these two, I get kind of a net change, right? In and out, it cancels out, and I'm left with just one thing. But remember, A prime, not A of t, that would give me amount of water. This is going to give me the rate of change, because I'm asking if it's increasing or decreasing. So I'm simply going to subtract R at t of 3 hours. R of 3 minus D of t happens to be negative. And again, you plug it into your calculator. So because R of 3 is less than D of t, that means the rate at this instant, t is equal to 3, the rate at which water is flowing in is less than the rate at which it's flowing out. Now, of course, this question is worth 2 points. You get the point for considering R of 3 and D of t, and of course the other point from your answer and the reason behind it. But you have to understand, again, these are rates, so when I subtract these two, I'm going to get an overall whether it's increasing or decreasing. Next question, C. It's asking for at times between 0 and 8 where the amount of water is a minimum, right? And in this case, we're going to solve for t at what time. The fact that this is closed parentheses, right, and underlined between this inequality or equality tells us that we're going to use a t-chart method. Because also, they don't ask for a relative minimum, they're asking for a minimum, in some sense the absolute minimum. And I guess the big giveaway is, again, this closed parentheses. When you see closed parentheses and a minimum, you know your first approach is going to be a t-chart. So here's what I have here. Anytime you make a t-chart approach, your t-chart is going to be the interval they give you, right? We were concerned with from t is 0 to 8. So my first 2 points are going to be 0 and 8. My next point is going to be the critical point. Now again, for a critical point, the derivative must equal 0. So again, I have that before, right? R of t minus d of t is equal to 0. Put that in your calculator, you have 0 and 3.272. Where we have 0 there, so we just add this extra point here. Now here's where things change. Instead of plugging these values of t into your rate, you can plug them into your original function and find which of these heights on the graph is the lowest for your absolute minimum. Now you're looking at these numbers and you're wondering where you get them from. Well, you kind of have to make your own function, your parent function, because remember, we're able to figure out what a prime was, so what's a of t, the original function? Well, to undo a rate, just like we did in part A, to undo this, we need to take an integral of both sides. That's kind of exactly what I did here. A of t is equal to integrate this side, and I get a of t, but what I do to one side, I do to the other side. So I'm going to take the integral of this. Normally it would just look like this, but because this now becomes a function, it's going to be an integral from 0 to t of these two rates, plus 30, because remember in the problem, the very last thing they say is that there is 30 feet initially at time of 0. So again, a big concept is knowing that you're going to use an integral, and by making it into an integral, and you have a of t on one side, this becomes a function, right? An integral function where you plug in t. Because let's say you plug in t of 5, you get cubic feet period, not cubic feet per hour or anything else. You get the amount at the end. Remember, plus 30, of course, but this part won't really matter. All you have to do is plug in t here, 0 and 8, and your critical point, and you get these amounts down here. Now obviously when you're using the t-chart method, you go with the one that's lowest, so our amount of water in the pipe is at a minimum at t is equal to 3.272. For this particular question, it was worth 3 points. 1 point for subtracting r of t minus d of t and is equal to 0, so essentially letting the rate equal 0. 1 point for the answer, and finally 1 point for the reason why you came up with this. Last question is asking us to write an equation, right, for when this equation we just made up from previously is going to equal 50. When is it going to overflow? And we know how to solve it. So I'm just going to go ahead and show you the answer here. Again, we initially start with 30, and we're solving for when the amount, not the rate, but the amount is equal to 50. So I'm literally just going to use what I had from part C, and all I'm doing is replacing the t with the w, because they want us to solve given the time w when it will begin to overflow or reach past 50. This equation by itself with the integral is worth 2 points, 1 point for the integral and 1 point for the equation.